All right, so here we are with lecture 4.6, second to the last lecture for Math 135. We're almost there. All right, so modeling with exponential functions. Okay, so pretty much these are word application problems using exponential functions. All right, so we're going to look at a few different ways that we can use exponential functions to solve problems in the real world. So the first one is a growth. Okay, so doubling time. So if we have initial size of a population, which we call n sub 0, and the doubling time is a, then the size of the population at any given time t would be given by this formula, where a and t are measured in the same time units. Okay, so for example, a and t would both need to be hours or minutes or seconds. All right, so a culture of bacteria has an initial population of 30, and it doubles every 4 hours. So the first thing we're going to do is find an exponential model for the number of bacteria in the culture after t hours. All right, so for a, we're given, let's see, what are we given? Well, I know that we have 30, so the initial population is 30, and it doubles every 4 hours. Okay, so we're looking at the time unit of hours. All right, so we know that A is the doubling time is going to be 4, and then the initial population, 30, is going to be n sub 0. All right, so if we look at our formula, n of t, the one right here, it's going to equal n sub 0, so 30, times 2, and then t to my a power. All right, not too bad. All right, so that right there is my exponential model for my word problem. So let's look at part B. We're going to estimate the number of bacteria after 20 hours. So we want to know the number of bacteria. So we want n of, we're looking at 20 hours. Okay, so our time is going to be 20. So n of 20. All right, well, we're just going to plug that into our formula right there. So n of 20, that's going to equal 30 times 2 to the 20 over 4. Okay, so we just plugged in 20 for time right there, t. Okay, so solving this, that's going to be 30 times 2 to the 5th power, which is 30 times 32, which gives us the answer of n of 20 equals 960. So, how many bacteria will there be after 20 hours? Well, there will be 960 bacteria after 20 hours. Period. Okay, so as usual, because it's a word problem, we answer in word form. All right, so the next problem. After how many hours? Okay, so now we're trying to find out t. That's the question. Find t. So after how many hours will the bacteria count reach 1 million? So we want to know the time when our bacteria count, n of t, is 1 million. Okay, so 1 million, well, we're going to have to write that one out. There we go, 1 million. So we're going to find t when n of t is 1 million. Well, I know with my function that n of t equals this amount here, so I'm going to set 1 million equal to my function. Okay, now this is interesting. Note, in our problem here, our variable is now in the exponent, so this makes it an exponential equation. Here's the fun stuff. Okay, so we're going to try to get our variable by itself, so let's divide by 30. And I'll simplify the zeros while I'm at it. And I'm also going to rewrite this value as 10 to the 5th. Less to write. All right, well, my variable is up in the exponent, so to get it down, remember, we're going to log both sides to get that apple out of the tree. So logging both sides. I could use log base 10 or log base e. Since I have that 10 there, I might just go with log base 10, the common log. All right, and then using that, that's how we can bring our exponents down to the front. Okay, last thing we want to do is get, let's see, well, actually, no, we have two things we got to do. We got to get rid of this log 2 times my t, and as well get rid of that 4. So let's multiply both sides by 4 to get rid of that 4 from that side with my variable. And what do I have? I have 4 times log of 10 to the 5th over 3 equals t log 2. All right, let's restart our work over here. The arrow indicating where my work goes so my readers can follow my work. Okay, so notice one thing I want to mention. Remember, when we're using equations, the only equal signs we have are the given one in the middle. All right, we do not continue with equal signs on the side. That would be if I'm using an expression. Okay, and also notice because we're with equations, our work tends to follow a vertical pattern, okay? Not horizontal across this way. It tends to follow a vertical pattern, just from top to bottom. All right, mini lecture spiel over. Let's continue. All right. And last thing, we're going to get that log 2 to the other side. Let's divide by log 2. And voila, our t is by itself. Okay, but the question is, should we leave our answer like this for a word problem? Well, I think if your fellow human asked you how many hours it would take for the bacteria to be 1,000,000, and you told them, well, it would take 4 times log 10 to the 5th power divided by 3 divided by log 2 hours for the bacteria to reach 1,000,000. Most people wouldn't appreciate an answer like that. We kind of want to know time. So we're going to pull out our calculator and find that value. All right, so what do we have? We have 4. Let's see. Okay, 4. And you know what? Because I have a large amount in the top, I'm going to go ahead and put this in parentheses. So 4 log of 10 to the 5th down divided by 3. Okay, and close that in parentheses. And then divide that by, I'm going to put it in parentheses, log 2. Close parentheses. A lot of parentheses. And there we go. Okay, most humans would appreciate an answer like this. If I said, how many hours would it take the bacteria to reach 1,000,000, and you told me 60 hours, I'd be able to comprehend that way better than if you had told me this answer. All right. Okay, so it will take 60 hours. For what to happen? The bacteria to reach 1,000,000. All right. Okay, notice I added that extra phrase there for the bacteria to reach 1,000,000. So if you just say it will take 60 hours, try to make that complete with adding what we're looking for the bacteria to reach 1,000,000. All right? Sorry, I keep tilting the page there. Okay, so there we go. That was exponential growth, where we had doubling time. So now we're going to look at exponential growth with a relative growth rate. Okay, page 2. All right. So a population that experiences exponential growth increases according to this model. Okay, same one we were looking at. Well, a little different than the one we were looking at. Okay, this time we have E. Before, we had 2, because notice that was for doubling time. This one, we're looking at exponential growth, so we're using E. All right, so a different function. So where n of t is the population at the given time of t, n sub 0 is the initial population, all right? So when we start looking at this stuff, n sub 0 is the initial population when we began charting it. R is the relative growth rate, and t is time. All right, so the population of a certain species of fish has a growth rate of 1.5% per year. The population in 2010 was about 10 million. All right, so part A, find an exponential model for the population T years after 2010? All right, well, let's see. What do we know? We know there's a growth rate of 1.5% per year. Okay, what was growth rate? Well, growth rate was R. So we know R is 1.5. I'm going to use that. We don't use percentages in our problem solving, so we're going to just change that to a decimal, 0.015. You could do a fraction. All right, and then what else do we know? We know the population in 2010 was about 10 million. Okay. But notice, we want a model starting at the year 2010. Okay? Because T starts after 2010. So our beginning time is at 2010. So this means 10 million is my initial population, because that's when we start this function. Okay? So n sub 0, my initial population is 10 million. Okay? Because that is when we decide to start this function, T years after 2010. All right, so our formula, n of t is going to equal, well, we need n sub 0, which I said was 10. Okay, and so notice this equation is going to be in terms of millions. Okay, and then E, well, we already know what E is. E is actually a number. R, my rate, is going to be 0.015 times my time. All right, there we go. Our exponential model, T years after 2010. So B, we want to estimate the fish population in the year 2015. So fish population, what is that? Well, that's n of t. So we want n of t when t is, okay, 2015. So am I going to use t as 2015? Is that the number I'm going to use? And you should be saying, no, that's not what we're going to use, because remember, I set up my model using 2010 as the beginning point. Okay, 2010 was my initial value. So the question is, 2015 is how many years after 2010? Well, that's 5 years. Okay, so we want time being 5 years after 2010. All right, so careful, watch that. Make sure you're correctly counting how many years after your initial value. So in essence, we want n of 5. All right, let's use our formula right here that we used, or that we got, sorry. That's going to be 10 times e to the 0.015 times 5. All right. So plugging, I'm going to figure out what that value is in my calculator. So that's going to be, let me see if you guys can see that calculator. All right. 0.015 times 5 is whatever that is, 10 e to the 0.075. Okay, so simplifying that out, let's just plug that into the calculator. Why not? So that's going to be 10 times, let's see, where is e? There we go, it's in blue. On our calculator, it's in blue, so that means I need to hit second, the blue key, second, and then ln. There's my e. E to the, well, 0.075. Enter. Aha. All right, I'm just going to round over 2 decimal places. That's what I do unless asked otherwise. So that's approximately 10.78. All right, so what is our answer? Well, in the year 2015, what do we know? The fish population will be, or is, let's see. I'm going to go with is, why not? That's technically in the past, or was, if you want to. The fish population is 10.78 million. Okay, remember we're using the units of million. All right, and there we go. Not too bad. Okay, so one thing I always find is helpful is to circle the given information and write out what we actually know. Okay, I find that really helps clarify my work for myself. All right, so next one, radioactive decay. This one's kind of fun. Okay. So, m sub 0, so if m sub 0 is the initial, so the beginning mass of a radioactive substance with a half-life of h, then the mass remaining after time t is modeled by this given function. Okay, so what is half-life? Well, half-life is the time it takes to fall to half its original value. Okay, so half-life is actually a time value. Okay, so when we ask for the half-life of a substance, we're asking how many years does it take for my substance for the mass to be half of its original value? Okay, half the original size of that mass. All right, so example 3. After 4 days, a sample of radon 222 has decayed to 62% of its original amount. What is the half-life of this radon 222? All right, so what do we know? Well, we know that we're looking at 4 days, so we want time to equal 4 days. And we know that our radon has 62% of the original amount. And the original amount is m sub 0. Okay, I don't actually know the original amount, but I do know that it's 62% of the original amount. So if I was to rewrite this little phrase here in mathematical language, that would be 0.62 times MO. Okay, because remember, of is the word for multiplication in math. All right. So we know this information, and what are we trying to find? We're trying to find the half-life. Okay, we're trying to find h, the half-life. Okay, so well, starting with our original function, we know that m of t is going to equal m0 e to the negative r times our time, which is 4. Okay, and so what do we want? We want h when m of 4 is 0.62 MO. Oops, squeezing that in. Oh, I jumped the gun a wee bit here on this one. That should still be T. So what do we want? We want h, half-life, when we know that m of 4 is 0.62% of the original mass, or the initial mass. Okay, well, I know if I plug in m of 4, that's going to be m sub 0 e to the negative r times 4. And we know that m of 4 is equal to 0.62 MO. So we're going to swap that out, substitute in 0.62 m sub 0 equal to m sub 0 e to the negative r4. Well, let's see. Let's simplify this. We have m sub 0 on both sides. So I'm going to go ahead and divide out by m sub 0 to cancel out that m sub 0. And I'm left with 0.62 equals e to the negative r4. All right. I am a little concerned, though, because notice, I don't see the variable h anywhere in this equation, and I want h. Let's look at this real quick. Oh, okay, look. R, which I do have in my equation, r equals the natural log of 2 over h. Okay, so at some point I want to substitute this value in for r. We could do that right now, but the reason I'm not doing it right now is because if I did that, I'd have an exponent that's a fraction. And that's going to be a lot of work writing, okay? Everything's going to be everywhere. So for now, I'm just going to solve for r. And once I get r by itself, then I will replace it with this fraction. Okay, that's my goal. All right, let's see. Solving for r, we're going to take the natural log of both sides. Why did I choose the natural log? Because I see e. Okay, because of that, natural log will cancel with the e, and I'm left with the natural log of 0.62 equal to negative r4. Okay, we're going to divide both sides by -4 to get that r by itself. Now I'm going to just move to this side because I have one more part for this problem. All right, so that's going to be negative natural log of 0.62 divided by 4 equal to r. All right, but we were not trying to solve for r. We want to solve for h. But, however, we do know that r is the same as natural log 2 over h. So I can switch that out with natural log 2 over h. So let's see, natural log of 0.62 over 4 equals the natural log of 2 over h. Okay, so let's see, cross multiplying, I get negative h natural log of 0.62 equals 4 ln 2. That was cross multiplying. Then dividing, I get h equals negative 4 ln 2 all over natural log of 0.62. All right, but as usual, h, remember, half-life is in terms of time. And most of us would not thank you if you told us time in terms of natural log. So we're going to pull out our calculator to figure out a value most of us humans would understand. So let's see, put everything in parentheses, so -4 natural log of 2, close that up, divided by, open parenthesis, natural log of 0.62 is 5.79. Okay, as usual, rounding up from 2 decimals, which is what I normally do. It's going to be 5. Well, rounding that up, that'd be 10, so 5.8. All right. So, what is our answer for this problem? Well, this is the half-life. So what do we know about the half-life? That's the time it takes to fall to half of the original value. So it takes approximately 5.8 days to reach its half-life. So sorry, that's rather vague. Let's not use the word it. Let's say Redlin 222. Redlin 222 takes, all right, approximately 5.8 days to reach its half-life. Okay, try to avoid using the word it in a word problem. Use the actual item we're talking about, which is Redlin 222. All right, one more part, and we're done with this page. Ooh, that was a rather ugly line. Okay, B. How long, let's go up here. How long will it take for the sample to decay to 20% of its original amount? Okay, so now we want to know time, how long. So we want time when we have our initial mass, so m of t, equal to 20% of the initial amount. And remember, we know that this, rewritten in mathematical language, is going to be m of t. Okay, so notice, if I am going to have an equation moving horizontally, I use this implication sign. It's not an equal sign, it's a little different.